Okay, this is a review of electric potential. You should know all this stuff already. You should not have to take any notes. Okay. Test charges that are high potential have high potential energy, and if it is at low potential, has low potential energy. Further, the electrostatic force does positive work on the charge to transform the potential energy into kinetic energy when it moves from high to low potential. Now, you should know what test charge means. That means a certain type of polarity that's positive. Now, of course, these would just be the exact opposite if we were talking about a negative charge. Negative charges naturally go um, from high potential to low potential. From low potential to high potential. That's what a negative charge naturally does by itself. And so you would have to do external work to it to move it from that high potential down to a low potential. So by definition, the potential energy A, VA, is potential energy at A per unit charge. So potential and potential energy are very much related. They are not the same thing though. Potential energy per unit charge is defined as potential or voltage. So therefore VA is equal to UA over Q, where UA is the potential energy. And we know that you can calculate the change in potential energy when it goes from one place to another by just simply taking the charge times that voltage differential. When it changes from a high potential energy to a low potential energy, it's going to be losing energy in the form of potential energy. Well, that means that the electric field is doing work to it, and that's converting that potential energy into kinetic energy. So change in potential energy would be equal to negative work. Relationship between the potential and the E field. The effects on any charge distribution can be described either in terms of the electric field or in terms of the electric potential. Electric potential is often easier to use because it's scalar as opposed to electric field, which is a vector. So electric fields are very difficult to work with because you have to look at the x components and the y components. You have to add them up vectorially. Whereas a scalar, you just look at the absolute sum of the things and add them together. It's much easier. You don't have to worry about any directions or anything. Recall that work equals force times distance times cosine of the angle between the force and the distance. Since negative work would be equal to a change in potential energy, the change in potential energy would therefore be equal to negative force times distance times cosine of the angle between them. If I want to figure out this change in potential energy, that would really be the potential energy at one location, B, let's say, which is here in the picture, minus the potential energy it had over here at A. So if this is a test charge, it's going from high potential to low potential. Remember, the electric field lines point from high potential to low potential. That's going to be equal to negative integral from A to B, the force times the line elements, dl. If I divide both sides by charge, this becomes the voltage, or I should say the electric potential at B minus the electric potential at A, equals negative integral from A to B of the E field times the line element L. So let's look at a very simple case where we have a uniform electric field. Uniform means the electric field lines everywhere throughout here would be parallel and it would be constant. So for instance, let's look at a parallel plate capacitor. We know the voltage from B to A. We know that B's voltage is exactly 50 volts lower than A's. So this plate over here, the positive plate, is 50 volts higher than the negative plate. And they're separated by 5 centimeters. So VB minus VA equals negative integral from A to B of E dot dl. I'm going to rewrite this VB minus VA as VBA. Now this E field is constant, so I can factor that out of the integral. And then all I have to do is sum up the line elements over here. Well, that's just simply the distance when I sum that up, because the integral of dl is going to be L, and when I go from A to B, that's the distance, which is 5 centimeters. Of course, that need to be put in meters. I'm going to go ahead and plug in the negative 50 volts and the 0.05 meters and solve it for the E field in between the plates. And I get 1,000 volts per meter. So now we know there are two possible units for the E field. It's volts per meter, or it could be newtons per coulomb. Let's look at another example. Let's find the E field and the potential as a function of R for a charged conducting sphere of radius R naught. And we're going to be looking at R is greater than R naught, and we're going to look at R less than R naught. The total charge on this sphere is Q. Start off with the E field. So for the first part, R is greater than R naught. Gauss's law gives us E is equal to Q over 4 pi epsilon naught R squared. Let's find the potential now. So the potential from A to B, so here's A outside to B, is integral of negative from B to A E dot dl. So we're looking at the electric potential here compared to out here. And the Q over 4 pi epsilon naught, that's all constant, so I'm factoring that out. And I have dr over r squared, and I'm summing that up. Doing anti-differentiation of that would give me r to the negative 1 power over negative 1. The negatives cancel, and I get a positive Q over 4 pi epsilon naught instead of the negative. And I have to evaluate this at RA and RB. Again, the reason it's the first power here is when I do anti-differentiation, it increases the power by 1. It used to be r to the negative 2, now it's become r to the negative 1. Okay, well, let's take this to the extreme where b goes to infinity. So if I do that, plug in infinity right here, that's going to be 1 over a very large number, in fact 1 over infinity, and that becomes 0. And so the voltage at A becomes Q over 4 pi epsilon naught 1 over RA. If we're looking at right at the edge here, the sphere, then RA is really R naught. So now we can go ahead and plot these for outside the sphere. The E field is an inverse square function, and the voltage is an inverse function. Now let's look at inside the sphere. Well, inside the sphere there isn't any charge enclosed, so the E field is 0. Now the potential from the origin to compared to R naught would be the negative integral from 0 to R naught E dot dl. The E field is 0, so that means the change of potential would be 0, which means the potential at the origin has to be the same as the potential at the edge here. So for the E field, it's going to be a 0 constant, but for the potential, it's a constant up here where it left off at the edge of the sphere. Okay, so now let's look at another spherical conductor, but now we have a nested set of spherical conductors. And there's a charge of, on the inner sphere, we have a charge of positive Q, and on the outer sphere, we have a charge of negative Q. And we want to figure out the potential as a function of R inside, in between the two spheres. Okay, determine the potential as a function of R. Okay, so we have to start with Gauss's law. And if we're looking at the region in between the two spheres, you can see kind of my Gaussian surface there. Well, the charge enclosed there would be positive Q. And so it's going to be over 4 pi epsilon naught R squared. Now let's find the potential between those two spheres. And notice the Q over 4 pi epsilon naught, again this Q right here is the positive Q. That's all constant, and so I can factor that out. I'm going to be going from B to A. This is going to be a higher potential because it's at the positive and this is the negative one. Again, when I integrate 1 over R squared, it becomes negative 1 over R. The negatives cancel, gives me a positive. And so I'm evaluating between A and B, the radius. And so there's my answer. If I know what the radiuses are, I can go ahead and plug in, and I'd figure out the voltage between the two. Let's look at another one. We have a cylindrical conductor, and these are nested cylinders. So we have one cylinder out here, has a bunch of negative charge on it, and we have another cylinder in here, a bunch of positive charges on it. And they're exactly opposite. So this is positive Q in here, and this is negative Q out here. So again, we use Gauss's law to sum this up. Now the area this time of my Gaussian, which is kind of hard to see, but it's right in here, in between the two. That's where we're looking at. We're looking at in between the two. Is going to be equal to the area of the outside portion of that cylinder. So it's going to be 2 pi r of the Gaussian times L. The Q enclosed is going to be the Q of that inner cylinder, which is positive Q. Now we can go ahead and figure out the potential between those two nested cylinders. And so we have negative Q enclosed over 2 pi epsilon naught L. I factored that out because it's constant. I'm going between B to A because I know A is the positive, or this is where the positive is. I know this is going to be the greater one. I could have went the other way, but I decided to go this way from B to A. And the only thing I'm integrating is from dr over 1 over r, or excuse me, 1 over r times dr. Now when I integrate this, that's going to be natural log. So I can't really get rid of the negative like I did before. I can get rid of this negative sign by reversing the constants of integration, and that's what I'm going to do here. And when I integrate 1 over r, I get natural log. So notice I reverse the integration constants to get rid of the negative sign. And so I get natural log of r, plug in b and plug in a, so it's going to be natural log of b minus natural log of a, and use properties of logs, that'd be natural log of b over a. So that's the potential between those two nested cylinders. Okay, so now let's look at a potential due to point charges. When calculating the work done to move a test charge, we can make the following simplification. So we're looking at VA minus VB equals negative integral from B to A E dot DL, what we've been using for quite a bit. Again, this is C exam stuff. This is not really B exam stuff. Okay, so if it's a point charge, that's going to be Q over 4 pi epsilon naught r squared. And when you integrate the 1 over r squared, you get negative 1 over r. That negative cancels the negative out front. And so therefore you just get Q over 4 pi epsilon naught, 1 over r minus 1 over rb. If you're a B exam person, this is kind of what you would use right here. You wouldn't use this integration at all. Now, if we want to figure out what the work done needed to move this charge from B to A by an external force, realize that that's going to be related to the change in potential energy. So if I take Q times the change in electric potential, this VA minus VB, that would give me the work done, or it's related to the work done. Okay, so, and notice here this is not negative. Well, that's because we're talking about an external force. If we're talking about the electric field converts that potential energy into kinetic energy, and so that's where that negative comes in. But if we're talking about by an external force, then we're just going to look at the force times that distance, which is going to be in a positive amount. So if the field does negative amount of work, then the external force is going to do positive. Vice versa, if the field does positive work, then the external force does negative. So if we know what the potential is right up here, we can multiply by the charge, and this is the relationship we get. Now realize this 1 over 4 pi epsilon naught, that is K, Coulomb constant K here. So I've just distributed that through, and we also have the Q here. So KQ over RA is the same thing as before, and then KQ over RB is what this is right here. But I'm multiplying it by this charge that's being moved, this point charge. test charge. And if this external force is going with the field, this will end up being negative work. And if it's going against the field, it would be doing positive work. So in other words, if this test charge is moving from a high potential to a low potential, something it would do naturally, kind of like you going downstairs with a crate of books, the amount of work you're doing is negative. If, on the other hand, you're going from low potential to high potential, going up the stairs, then it's going to be positive work. So that's the work that an external force does. What about the work that the field does? Well, the field's doing positive work when it goes from high potential to low potential. Think about the direction of the force from that field. It's from high potential to low potential, and that's direction is moving, so it's doing positive work. Whereas if it's the charge is moving from low potential to high potential, this test charge, which means it's positive, then the force is from high to low, but it's moving the opposite direction, and so then it would be negative. Then you have to think about, what if this isn't a test charge? What if this is a negative charge? Well, then again, the answers are going to be just the opposite. So you really need to be thinking, what kind of charge is this, positive or negative? How is it moving from high potential to low potential, or vice versa? And what force are we talking about here? An external force or the force from the field? Okay, now let's figure out the minimum work that must be done by an external force to bring a charge which is positive 3 microcoulombs from a great distance away to a point that's 0.5 meters away from a charge that's positive 20 microcoulombs. So there's my 20 microcoulomb charge just sitting there. And I've got this other charge sitting out at infinity that I'm going to be bringing in. So if we're looking at the electric field lines from this positive charge of 20 microcoulombs, they kind of point outward like this. And of course we could draw a whole bunch of equal potential surfaces so that it kind of looks like a topographical map that I'm looking down on, and this would be a mountain. I'm going to take this positive charge from infinity and bring it closer to this positive charge. I'm going from low potential to high potential. And I'm looking at the external force. Well, it's going to take some external force to push this uphill. So the amount of work I'm going to be doing here, this is definitely going to be positive. The amount of work that the electric field is doing is negative because the force is in the opposite direction from the field. It points along the field lines and it's going in the opposite direction. So, but I'm looking at the external force, so it's definitely going to be positive. So the neat thing about this is, yeah, I could look at all these field vectors and everything, but it's really complicated because it cuts across them at some angle. It's easier to look at it in terms of equal potential surfaces. Now we saw it move in, let me back up, we saw it move in kind of like this. It could have also moved right along the field line up to the equal potential line and then over. If it moves anywhere on an equal potential surface, there's no change in voltage on that equal potential. No work is needed to move it along at equal potential. So really all I need to do is I need to figure out the difference in potentials. So this is a field charge, or excuse me, this is a point charge. And so therefore it sets up this equal potential surfaces where it's given by the voltage way out here at infinity is given by KQ over RB. And the potential here, let's say that's A, is given by KQ over RA. That's the potential. And if I want to figure out the work, I have to multiply that quantity by the charge of this thing that I'm moving, which is 3 microcoulombs. I could plug this in. Of course, RB was an infinity. That's where it started at, and so that would end up being 0. Plug in the numbers, and I get the work done by this external force is 1.08 joules. How much work is done by the electric field in this case? Again, that should be 1.08 joules, but it's going to be negative. Think about what your answers would be if we were moving a negative charge instead of a positive charge. Okay, so now I really want to drive home to you guys what the difference is between looking at electric fields, which are vectors, and looking at electric potentials, which are scalars. Okay, so I've got these two charges, Q1 and Q2, both 50 microcoulombs, but this is negative and this one's positive. And I want to figure out the electric field at points in space of A and B. And I want to figure out the electric potential in spaces at points A and B. Okay, so let's look at that. Well, if I'm looking at the electric field vector at A, there's going to be two electric field vectors. One from particle 1 over here, and since it's a negative charge, the electric field vector points into it. I'm going to call that EA1 because it's at A and it's from charge 1. And this one is from a positive charge, points out of it, and so this would be EA2. Okay, you can definitely see those are at angles one another, so I'm going to have to worry about angles here since these are vectors. So I'm going to go ahead and break this EA1 into an X and a Y component. The X component would be given along here. Notice this angle here is the same as this angle. Okay, so then if I want to figure out the X component, that would be given by the electric field vector times the cosine of the angle. This EA2 doesn't have an X component, so I only have one X component direction. And cosine of the angle theta would be given by the adjacent over hypotenuse, which would be 52 over 60. And so the E field is KQ over R squared. So 52 over 60 reduces to 13/15. And we have K coulombs constant times a charge of 50 times 10 to the negative 6 coulombs over the distance wave, which is 0.6 meters squared. And if you simplify that, you end up getting 1.08 times 10 to the 6 newtons per coulomb. Okay, now let's figure out the Y component. There's going to be two Y components. There's the Y component from the charge 1, and it's downward. And of course, there's this Y component from charge 2. In fact, it's all a Y component there. So I'm just going to call that EA2 instead of putting subscript Y. They're in opposite directions. This one here is going to be positive. I'm going to make that one negative just because I chose it to be that way. So if I want to figure out the total Y, it's going to be EA2 minus EA1 times the sine of the angle theta. So sine of theta is going to be given by opposite over hypotenuse, which is 30 over 60. And then, of course, how do I find the E field? Well, for E field of 2, that's going to be KQ over R squared. And then EA1 is going to be KQ over R squared. The 30 over 60 simplifies to 1/2. I didn't put the 1 here, but you can see the 2 down in the denominator. And now simplifying, I get 4.37 times 10 to the 6 newton per coulomb. And then I want to do Pythagorean theorem because I want to figure out what the overall vector is when I combine both of these EA1 and EA2 together. So that's going to be a square root of the X component squared plus the Y component squared. And to find the direction, the angle, it's going to inverse tangent of the Y's over the X's. The sum of the Y's over the sum of the X's. And when I do that, I get 4.5 times 10 to the 6th volts per meter, or newtons per coulomb, either way, at 76 degrees above the horizontal. Okay, now let's find the potential at A. The potential at A would just simply be the potential from 1 plus the potential from 2. Don't have to worry about any X and Y components. Remember that for my point charge, potential would be equal to Q over 4 pi epsilon naught R, or said another way, 1 over 4 pi epsilon naught is really K, Coulomb's constant, so KQ over R. Plug this in, we get KQ1 over R1A plus KQ2 over R2A. Now C exam people would have to be able to derive this using Gauss's law and then integrating. B exam people just kind of have to have this memorized. Okay, so then we can go ahead and plug in. Now the difference between the potentials and the electric field is for the potential, or excuse me, for the electric field, we do not put in the polarity of the charges, but for the potential we will. So Q1 is going to be negative, Q2 is going to be positive. So plug in K, Q1 over the distance plus K, Q2 over its distance away from A. Simplify, we get 7.5 times 10 to the fifth volts. That's my answer. Much quicker, much easier, because it's scalar as opposed to vector. Okay, now let's look at B. If I want to figure out the electric field at B, I have to look at the two electric fields from the two charges. So from charge 1, the electric field is going to be pointing along the line toward this negative charge. And from charge 2, it points away from this positive charge up this direction. So there they are. The E field at B from 2 points that way, away from the positive charge. And the E field at B from 1 points towards the negative charge. The angles here, this angle here is the same as the angle down here, and that's the same as the angle over here, because this is 26, 26. This distance here must be the same for both triangles, and therefore this distance is going to be the same as this one. Okay, so let's start off with the x components. There's going to be two x components here. There's going to be from charge particle 2 and from charge particle 1. And they're both in the same direction, so I'm going to be adding them together. So the total x component is going to be given by EB1 times cosine of the angle plus EB2 times cosine of the angle. Okay, cosine of the angle is going to be given by adjacent over hypotenuse, which is 26 over 40. These two, EB1 and EB2, they're the same length. And the reason I know that is because they both have the absolute same magnitude of 50 microcoulombs, and they're the same distance away. So that would be the same as just having one of the E fields and multiplying by 2. So let's say 2 times the x component of this field. And 2 over 20, or 2 over 40 would reduce to 20 there, so I have 26 over 20 times kq over the distance away squared. And so the x component is given by that. I didn't simplify it. The y components, notice the y components are in opposite directions. They'd be the same length. They cancel, so that means the y is going to be 0. Wow, this is slightly easier than finding an A, but not as simple as figuring out the potentials. Okay, now I have to do Pythagorean theorem. And when I do that, I get the E field at B equal to 3.65 times 10 to the 6 volts per meter. And the angle is going to be 0 degrees. In other words, right along the horizontal in the positive direction. Let's figure out the potential now. So this is going to be KQ1 over R1B plus KQ2 over R2B. Plug in the charges. Don't forget the polarities. And I get 0. It makes sense. They're the same distance away. One's positive, one's negative. They're going to cancel out. So the potential right there in the middle, in fact anywhere along that y-axis, is going to be 0. That's because same distance away and same magnitude but opposite polarities. Okay, one last problem. Let's calculate the work done by an outside force to assemble a hydrogen atom. So a hydrogen atom is consistent of a proton, and I'm going to say that has a charge of positive E, E symbolizing the charge on an electron. And I'm going to bring in this electron from infinity somewhere and put it together to put it in this hydrogen atom. And when the electron's in its ground state, its distance from that proton is 0.529 times 10 to the negative 10th meters. So put it in here and it starts zipping around, let's say. Okay. So we know that if I want to figure out the work, change in energy of that system would be equal to the work. So the only way you can change the energy of the system is if you transfer energy in or out. And in this case, the only way we're going to be transferring it in or out is through work. The change in energy of the system, there are twofold. There's kinetic energy changes, and there's potential energy changes. How do I find change in potential or kinetic energy? Well, that's final kinetic energy minus initial. Same thing for potential energy. Final potential energy minus initial. Well, the initial kinetic energy, when it's at infinity, it's not moving that electron, so zero kinetic energy. Further, at infinity, it has no potential energy, because think of it as kq over r. The distance goes to infinity, so that potential energy then goes to zero. So we're really looking at the work done is going to be equal to final kinetic energy plus the final potential energy. How do I find the potential energy? Well, that would be equal to charge times the final potential, electric potential, the voltage. And how do I find that? That would be kq over r, where r is the distance to the proton. This q here is going to be the charge of the proton, which happens to be the same as the charge of the electron, except it's positive e. This right here, negative e, that stands for the electron's charge. Now we need to figure out what is the kinetic energy of this electron going around there. So that means we need to know something about its speed. Well, how can we figure that out? Well, let's assume that it moves at a constant speed, and let's assume that it's a circular orbit, kind of like I'm demonstrating. Those are a couple assumptions we don't know, but let's just try that. Well, if that's true, we know something about circular force. We know something about circular motion. We know that there is a force that's directed toward the center. Something has to provide that force. Well, what's providing the force is going to be the electrostatic field. So if I set the force from the electrostatic field equal to the net force, and I plug in the mathematical model for the net force, mv squared over r, and I plug in what that force is from Coulomb's law, kq squared over r, kq1 times q2 over r squared, where q1 and q2 are the same, that's why it's e squared. Then I can set those two equal and figure it out. Well, one of the r's cancels, and so I get mv squared is equal to k times q1, q2, which in this case is e squared over r. Notice this mv squared looks kind of like kinetic energy. What would I have to do to that to get kinetic energy? If I divided it by 2, that would be the formula for kinetic energy, 1 half mv squared. If I divide the right-hand side by 2, I have to divide the left-hand side by 2. So the kinetic energy is going to be k e squared over 2r. Let's go ahead and plug that in to the equation. I'm factoring out the e here so that I can combine stuff. So notice there's an e here. I just simply factored it out. It's the same relationship. Now this kind of looks like the electric potential, except the denominators are not the same. In order to get the same denominator, I'd have to multiply the electric potential energy by 2, actually 2 over 2. Simplifying it, I get the work is equal to negative E times KE over 2R. I'm going to plug in what the charge of an electron is. It's 1.6 times 10 to the negative 19th. I know what K is. I know R is. It's given to me. And I'm going to leave this in electron volts, which means I'm not going to plug in 1.6 times 10 to the negative 19th here. I'm just going to plug it in here to figure out the voltage. So the energy, the work needed to bring this electron in from infinity is negative 13.6 electron volts. We could have that in joules, but it makes more sense to leave it in electron volts. Notice the negative sign. That's because we're moving a negative charge towards a positive. It's going from this low potential up to a high potential. Negative charges naturally do that. That's what the electric field would want to do. It's doing positive work, so an outside force is going to have to do negative work. So this would naturally occur on its own. What's the ionization energy for this hydrogen? So ionization energy means how much energy would I have to apply to this electron to knock it out of its orbit and go all the way back to infinity? So how much input energy would I have to put into the system to get rid of that electron, to kick it out? That's what it means to ionize something, to separate out the positive charge or the negative charge away from that positive charge, to kick out the electron. Well, I'm hoping it makes sense that really I'm going to have to put in a positive 13.6 electron volts, because that force I'm going to have to provide is going to be going against the electric field. So That means I'm going to have to apply a force through a distance. I'm going to have to do work to do this. And positive amount of work equal to 13.6 electron volts. That's how much it takes to ionize it.